What we're going to do is learn about trig with an application to physics. When you learn about trig in math class this year, you're going to learn a lot. Okay, I'm literally taking the portions that you need for this class specifically for next chapter, which you aren't going to learn until the end of the math year for your Algebra 2 trig course. So, there's a lot of stuff I'm going to say, trust me, or just believe me if I say stuff like that, for now, that I'm answering because the explanation is much more in depth and would take many periods on its own just to explain it. So I'm going to go over the basic stuff and you need to follow along as I go through it. So you all know right triangles from geometry. And I'm starting with information that you do know. So draw yourself a right triangle. Okay, draw it the way I'm drawing it, please. I'm drawing it specifically like this because this year we're going to be looking at what if an object is launched at an angle. So imagine here's ground level, here's the object being launched at some angle, and it's going to follow a parabola. So we're going to be really looking at this angle right in here. Okay? Now, you've learned about Pythagorean theorem already, which is a squared plus b squared equals c squared, and that also relates to what's called sine, cosine, and tangent. And those are 3 buttons on your calculator you've seen all the time but probably haven't used yet. So let's start by simply labeling things, okay? I'm going to start by calling something an angle theta. There's a symbol, okay, which means theta. Theta. It just means unknown angle. You're going to see it a lot. It's a Greek symbol like delta or alpha, okay, or any of those symbols. And it simply represents angle. It's like, you know how everybody always uses x for an algebraic variable? Whenever you have an angle, or not whenever, but most of the time, you're using theta. You'll hear people say theta, solve for theta. When you hear theta, think angle, think angle. It's no different than the letter A, B, C, D. It's a symbol or a variable. Okay, just take my word on that. You're going to see it a lot. The symbol is written as like a 0 with a horizontal line through it that kind of inclines a little bit. Kind of goes up a little bit like that. Okay, that's how theta is kind of written. Some teachers will write it like this, you'll see, okay, just because they get lazy and whatnot, but it's just simply a horizontal line through a number 0, really. Now, if we know the angle theta and we know one other side, we can determine the other 2 sides. And that's the real beauty of trig when it comes to applying it to physics. So, with Pythagorean theorem, if we remember, we needed to know 2 sides to find the third leg. Always. You need A or B and B to find C, or A and C to find B, etc., etc. Here now, with trig, if we know an angle and we know a side, we can figure out the other 2 remaining sides without even using Pythagorean theorem. So, what I'm going to do first is start labeling things. What is this side of a triangle always called? Hypotenuse. Everybody, yeah. Hypotenuse. Always the side opposite the right angle in a right triangle is called the hypotenuse. We then label 2 other sides with respect to theta. We call those sides opposite or adjacent. Which side is opposite theta in this problem? The vertical side or the horizontal side? The vertical side is opposite theta. So we call this opposite. It's always, these words are always with respect to theta. Hypotenuse is always the same, obviously. Okay? And then finally, the other side is called the adjacent, meaning next to. Like 2 rooms that are adjacent are next to one another. This is next to the symbol theta. And it's not the hypotenuse, though, right? So if I suddenly move theta to the upper angle, opposite and adjacent would just switch. Again, if I knew theta and theta was up here, at this upper angle right here, then the opposite and adjacent would switch because this would be opposite theta, which would be up here, and this would now be adjacent to theta up here. So it's always with respect to the angle that you know. Now, let's do an example of this and how we actually go about this. There's an acronym that is very useful to memorize that you will need to memorize anyway this year in math. So you may as well. And it's SOHCAHTOA. Very good. Okay, SOHCAHTOA. Think of it in 3 parts, please. I'm underlining for you. Think of it in 3 parts. Okay? I've, in the past, told a stupid story about like a person that stubs his toe and soaking his toe, and it helps you memorize it. For the sake of time today, I'm going to let it go. Maybe if we have time next class, I will. Okay? But for now, take a look at this acronym. An acronym represents other words. SOH represents, the sine of an angle is always equal to what's called the opposite over the hypotenuse. And its acronym is what's spelling this out for me as I go through this. The second one, CAH, what do you think might stand for? Cosine of theta is adjacent over hypotenuse. And the last part, tangent of theta, if we look at the acronym and just follow the acronym along and use context clues, TOA, what's O and what's A?
Tan equals opposite over adjacent.
Good. The tangent of theta equals the opposite leg over the adjacent leg. And these are trigonometric ratios. They're just lengths. So if I knew the angle and I knew one of these sides, I could figure out the other side by solving the equation. But you're gonna need a calculator to do this. Jake, you had a question.
What is that third letter after CO?
That is an S for cosine. It's the abbreviation. Sorry, I could write out the word. So this is sine, S-I-N-E, really, the word. It's abbreviated S-I-N, like sin. Then cosine is abbreviated C-O-S. And then tangent is abbreviated T-A-N. I'm using the 3-letter root because on your calculator, if you take a quick look, you'll see S-I-N, C-O-S, and T-A-N all next to each other on the calculator. That's how they show up on there. So we're going to use that abbreviation, which you'll use in math anyway. But again, sine, cosine, and tangent. So again, this is just like any other equation. If I know 2 of the variables, I can find the third. So if I had a random triangle, any random triangle, and I knew the angle, I could plug it in, and I knew the opposite, I could plug it in, and then I could solve for the adjacent. All right? So let's go to an example to do this. Now, before we get to that example, change your calculator mode. Open your calculator up. If you don't have yours today, you should kick yourself in the butt later because you forgot it, but you should also do this later. Please bring them. Hit mode. And you're going to see that right now I have degree highlighted. You all should also. So go down to radian. If it's highlighted, go over to degree and hit enter. So the degree is highlighted and then just quit out. You're going to learn in math about something called radians this year, which is another unit of measurement. You know how we have inches and centimeters?
Yes.
There's degrees and there's radians. That was very enthusiastic. Yes, Ed. Awesome. So you have degrees and you also have radians. For the sake of physics, everything will be in degrees. You will not have to use radians. In math, you may look at radians this year. You will look at radians. So you have to know what mode your calculator is on when utilizing it. Okay? Let's go back to the question at hand now. All right, so we're back to the iPad now. Let's look at an example. All right, here's the example. Let's say we know the angle theta in this problem is 35 degrees, and we also know that the hypotenuse is 20 meters. All right, so we're looking at a structure, and we have to figure out the legs of that structure, knowing the angle of inclination, knowing that it's a right triangle, so let's draw in our right angle there. And we know that the length of the beam, or the ladder, whatever it may be, maybe it's a ladder up against the wall, the ladder is 20 meters in length. That's a long ladder, it's like 60 feet. Okay? And we're trying to figure out the length of between the wall and where the ladder hits the ground, or from the wall to where the ladder hits the wall, or the legs of the triangle. Now, you would start to think, okay, Pythagorean theorem, but why can't you use Pythagorean theorem? You only have one leg. You need 2 legs to find the third leg of a triangle if you're ever going to use Pythagorean theorem. So we can't do that. So we use trigonometry instead. Let's label these. Let's label this x, and let's label this y. How come I use x and y? Horizontal for x and y for vertical. Okay, just like we've done so far this year. Now, let's say we want to determine what x is. What is x with regards to adjacent, opposite, or hypotenuse? Which one is x in this case? Adjacent. And that's because we have this angle, remember. It's right next to that angle. This is always hypotenuse. And y is opposite the angle, so that's the opposite side. Now, let's say I want to find out what x is. X is adjacent. All right, so I've got the a part of it. I've got the hypotenuse, because it's 20, so I know that. So when I have adjacent and hypotenuse, which of these three functions includes adjacent and hypotenuse? The cos, or the cosine. Very good. All right, so we're looking at that middle one there. So we've got the cosine of 35 is equal to... Now, we write it the same way we would write it in the previous slide. Now, what's the adjacent in this case? Be careful. The angle is 35. The side length is the adjacent here, which is x. The hypotenuse, which goes in the denominator, is just 20. Again, I'm literally plugging into one of the three ratios, either sine, cosine, or tangent. I chose cosine, or Victoria chose cosine, because we were looking for x, which was adjacent. We had the hypotenuse, which was 20. So we have adjacent and hypotenuse right here, which tells us let's go to cosine. Now, if I'm trying to figure out what x is, how do I get rid of that 20 at the bottom? How do I get rid of that 20 at the bottom there, Jake?
Multiply.
By?
35.
Not the 35, be careful.
20.
By the 20. I got to multiply by the 20 because we're currently dividing by the 20. See how those two cancel right there? So, focus, come on. So it turns out that x is just the product of 20 and the cosine of 35. Now, you cannot do these problems in your head. Soon you're going to learn that there are certain angles you will memorize in math class, but 35 is not even one of them. And the cosine of 35 is some decimal. Let's take a look at what it is on our graphing calculator. So I'm back to the computer now. So I take a look at the cosine of 35 just to see it. You could type it all in one line, but I just want you to see what it looks like. 0.81915204443. This is not a number that you're going to memorize. So you need to use your calculator. All right? So let's go back. Let's type in 20 times that, right? So 20 times the cosine of 35 is really what I should have typed in. I was just showing you the cosine of 35. All right, so when I multiply those, since the cosine of 35 is a decimal, it's going to be some number less than 20. And take a look, 16.38. So let's go back to our iPad. X turns out to be 16.38 meters. That's the short leg of the base of the triangle. Why else do I know that it's going to be less than 20? Besides the fact that we're multiplying by that 0.8. Yeah, hypotenuse is always long. It's very good, Paul. And the hypotenuse is 20 in this case. So it's got to be less than 20, the answer you get. If you get an answer for the leg that's more than the hypotenuse, you did not do something right along the way. You made a mistake at some point in time. Yeah.
I'm confused how we got the end there. It's 20 times the cosine of what?
Of 35.
Oh.
See that angle? It's always whatever the angle is goes in the cosine or the sine or the tan. Always the angle, okay? All right? Now, that gives us x. And obviously at this point in time, we could use the Pythagorean theorem and find out y. But just to make it more useful, let's use trigonometry again to practice. So if I wanted to find out y, let's take a look. I'm going to point on the diagrams. So I want to find out y, which is the opposite. I've got the hypotenuse. Again, I want the opposite. I've got the hypotenuse. I've also got the adjacent, but I'm going to ignore that. Make me let in for a minute. So I've got hypotenuse and opposite. Which of these three functions should I use for hypotenuse and opposite? Which one has an H and an O in it? Which one of those three, Kira? Sine. There's the opposite, and there's the hypotenuse. So I'm going to use sine. So I write sine of 35 equals opposite over hypotenuse. Mike.
I'm just confused on what we're finding now.
So we're trying to find out the legs of the triangle. So we first determined x, which was the base.
Yeah.
That was 16.38 meters by solving for x. Now we want to find out what the height is, the y value.
Oh, yeah.
So to find out the height, we say that the sine of this angle equals opposite over hypotenuse, which is y over 20.
Yeah.
And then we rearrange to solve for y. Okay, so we're determining the legs of a triangle right now without Pythagorean theorem.
So multiply by 20.
Yeah, so the same approach, very good. Let's multiply by 20 again. Kira.
Do you have to use this sine y if you already found x? Or are we just not using Pythagoras?
We're just not using the Pythagorean theorem. You're going to see why we'll use the Pythagorean theorem in class, but I'm showing you both ways just so you have a little, versatility. So let's multiply 20 times the sine of 35 on our calculator. Okay, and notice what I'm going to do. Please, don't retype the whole line. Just press second, entry, go over to cosine, let it flash on cosine, and hit sine. Makes it a lot easier, doesn't it? Okay, and then you get 11.47. So we've got all three legs of the triangle without ever doing any work as far as Pythagorean theorem is concerned. We were given a hypotenuse and an angle, and from that we were able to determine the other legs of the triangle. Okay, the other legs of the triangle. Now, if you're not given the hypotenuse, maybe you're given the opposite, you have to then rearrange it to find the other two. So let me give you an example that you could work on. Okay, that we can maybe do together once I give you a minute to try. Triangle in this case that had the following. All right? Say that's the triangle now. Do me a favor, please call this x, and please call the hypotenuse either h or r. You're going to call it r a lot in physics, so I'm just using that now. Okay, y is 8 still, right? So that 8 up top is still y. So if I want to determine the value of x and r in this problem, I have to look at my trigonometric ratios. I have to look at SOHCAHTOA. SOHCAHTOA. Now, if I take a look at my diagram, let's see, Steph, you want to find x or r first? It's optional, so whichever. X? All right. So if we want to find x first, which is x? Is x adjacent, opposite, or hypotenuse? Adjacent. X is adjacent. And we know the opposite. Again, if we're finding x, x is adjacent, and we know opposite. Josh, what do we got? Which one? 10. Josh has a 10. Very good, Josh. All right, so we've got 10 of 48 is equal to opposite over adjacent. Just pause at that point in time and look up, make sure you have the same thing I have. The tangent of 48 equals opposite over adjacent. Opposite is 8, adjacent is x. Now be careful when solving this. Think of the formula that we started the year off with to be analogous when solving. Remember how you would solve this for t? What would you do to solve this for t? What did I tell you guys to do? Switch the v and the t, right? So what should you do in this equation now? Yeah, switch this whole thing with this whole thing. Flip-flop. The whole thing. The whole thing. Okay, the entire expression always moves with it. So, Mike, if you had like x times y times z instead of tan 48, that whole x, y, z would all move with it. Okay, everything that's there always moves with it. So at this point in time, we've got x. It's 8 over the tangent of 48. So I go to my calculator. So I'm back to the computer now. 8 divided by tan 48, close parentheses, enter. And I get 7.2. All right, 7.2 is my horizontal length of the triangle. By the way, correct me, this should be a right triangle. Let's put a right angle on there. Now, you've got 7.2, you've got 8. If you want to use Pythagorean theorem to check, you can, but let's use trigonometry to find this solution. Use these two, please, on your own. Try and figure out R. Try and figure out R. Do it on your own for a second, then I'll go over it. I'll give you like a minute to do it. Try and figure out R. Please use 8 and R. Don't use the answer you got for X. Use what you have in the beginning every time, just to make it simple, in case you make a mistake. Remember that question, Miss?
Yeah.
In case you make a mistake, for this one, I would use the original answer. Just in case. Yeah. It would, that's right. Well, you have opposite, right? You have minus, which function? Sine, right? Use sine, make sure. Use sine for this one. Remember, you have 8, which is opposite. You're looking for R, which is hypotenuse. So opposite and hypotenuse is SO8. Okay? Please, you got it? So, you know opposite and adjacent, but that won't give you anything. You're trying to figure out. So once you have this, forget it. Hey, we'll pick up with this not tomorrow, but the next day. You're off tomorrow. Okay, so we won't look past the trig. We gotta get them still. Okay, so again, that's why we're looking at this setup this way. Again, X is our horizontal and Y is always our vertical. Now, in our problems in physics, what you're going to be given is an example where an object is launched at an angle. So imagine a football player or a soccer goalie or somebody in sports that is throwing an object in some parabolic motion or a parabolic path. Okay, the velocity with which you kick the ball or throw the ball or whatever it is not horizontal, it's not vertical, it's both. Right? It really is. Unless you're maybe a baseball pitcher. Okay, a baseball pitcher usually is only horizontal, but even curveballs dip. Okay? Soccer, for the most part, have some sort of spin to them, so they'll curl a little bit, they'll turn. Football is like the one where there's definitely two-dimensional motion for most passes and punts. Some passes in football will be, line drives, so they'll be mainly horizontal. So what we're looking at, though, is ideas where an object is launched at some given angle. And we call that angle theta usually. So let's pick a number. Let's say it's 28 degrees. Okay, the launch angle for this object. And the path it would follow, which you can just, write over the triangle if you want, just so you know what we're doing, would look like this. Okay, that might be the path of the projectile. Or, maybe a skateboarder going off a ramp. Skateboarder goes off the ramp. There's the ramp right there. The ramp has an inclination of 28 degrees. And it goes off at some sort of an angle. Now, when an object is thrown or launched or moved at an angle to start, it's moving both horizontally and vertically. Okay, and the easy way to remember this or to think about this, think about a simple example. If I had this tissue box, and I wanted to hold it against the wall, I could apply a force against the wall like this and just push. And my force would be in the X direction, meaning I'm pushing horizontally. If I wanted to hold it up against the ceiling, I could push up vertically, or if you're on the subway, where you have to hold on, you're holding vertically. But what happens when you have to push something at an angle like this? You're pushing up and you're pushing out. You're both pushing vertically and horizontally. It's like being on the subway when you're in that awkward position. When you're like standing over something like this and doing that, so you're not like all up against them. Yeah, it's like that. Your arm is at an angle. If you had the height to reach above, which I usually don't, okay, you can get that one above top. Or if you have the vertical pole, you can hold it like this. But when you have that other pole, it's always weird. So you're kind of pulling yourself up, but you're also pulling yourself over, right? So you don't move. So it's the same thing with objects that are launched. So this object that's launched, it not only has a vertical velocity, but it has a horizontal velocity. And the interesting part is this, the acceleration that we know of on Earth, gravitational acceleration, only acts vertically. So this problem we're going to see in a moment, that the vertical velocity changes as it goes through the path. When it gets to the top, it kind of stops for a second vertically, but it's still always moving horizontally. So we're going to see how we can distinguish between the two. And what's really important now is that we use this triangle, and we look at this triangle, and we come up with an expression for x. Okay, and in physics, what we're going to see is that usually this is going to be some velocity, so it would be like this. This would be your VI. Okay, and then we're going to end up trying to figure out what's called VIX and VIY, where IX and IY are the subscripts. Okay, those are not three variables. It's one variable, VIX, meaning the initial velocity in the x direction. And VIY is the initial velocity in the y direction. But that's really what we're going to try and determine, and it turns out that triangles are what enable us to determine this. So what we're going to try and do right now is come up with some sort of a generalization. And if we can figure out VIX and VIY right now with numbers, we can then extrapolate that, right? Take that idea and come up with that generalization that helps us to write down like a statement that will give us a way to come up with the vertical and horizontal velocities every single time. So let's remind ourselves, what was that acronym that we looked at for trigonometry? What was the acronym? Yeah, SOHCAHTOA. Okay. SOHCAHTOA. Now, if I wanted to find the VIX, the initial velocity in the horizontal or x direction first, I need to consider what that is as far as adjacent, opposite, or hypotenuse. VIX, Josh, is? Why?
It's not opposite.
It's not opposite. Good, that's an easy way to think about it too. It's not the opposite one. The opposite one is clearly VIY, because that's opposite to 28 degrees. When I say opposite and adjacent, I mean with respect to theta, with respect to the angle that we're given. The hypotenuse is always the long leg. Okay, this is always the hypotenuse. So if we were to determine VIX, what equation would I write to figure out VIX? And you don't have to give me the solution, but give me the setup. Which of the trig functions I'm going to use, what it would look like.
Would be comma.
Yes, so it would be CAH or cosine. Very good. So ca. Okay, so let's write this out. So cosine of the angle, which is 28 degrees, is equal to, and I literally read across, it's cosine equals adjacent over hypotenuse. I'm reading the letters in that order. So adjacent is what I'm looking for, and the hypotenuse is 14 meters per second. Okay? So that would be my setup if I were trying to determine the initial velocity in the x direction. That would be the setup I'd begin with. Now, if I wanted to find VIX, and I'm not even going to ask you to determine the number right away, okay, but you can check for sure. But if I wanted you to find VIX algebraically or solve, how would I get rid of that 14? Times both sides by 14, please. Okay, so simply put a 14 here and a 14 here. Okay, those clearly cancel. So it turns out that this is my expression for VI in the x direction. Okay, and I'll explain how this works in a moment. Once you see VIY, I think you'll pick up on the trend. Okay, so that's VIX. That's where I get VIX from. When I multiply both sides by 14, it turns out that VIX is equal to 14 times the cosine of whatever theta was. For VIY, go back to the triangle if you need to. For VIY, which of the trig functions will I use? Hint, we used cosine, so we're probably not going to use that one, right? And again, assume that you don't know this number. Assume you don't know VIX, even though you calculated it a moment ago. Use only what you know. Okay, what you know and what you're looking for. So I'm kind of giving hints here. Jake? Yeah, you would use SOH, because you know hypotenuse still, and you're looking for opposite. Okay, so SOH. And believe me, you're probably saying, well, why don't we choose Pythagorean theorem once we know two of the legs? If we come up with this today, you won't ever have to really do this again. Okay, you'll realize the generalization that we're going to make at the end, or the conclusion we'll draw. So yeah, we're going to use so, and that means sine. So I know that the sine of 28 degrees equals opposite over hypotenuse. Opposite again, that's VIY. That comes from right here. That's your opposite. Hypotenuse is 14 meters per second. So So that's over 14 meters per second. And again, how do I solve this one? The same way we solved the last one. Currently, VIY is being divided by 14, so I have to multiply by 14. I've got to multiply by 14. So when I do that, I end up getting 14 times the sine of 28. Okay, I'm going to move that 14 up by multiplying both sides by 14. Puts a 14 here and a 14 here. Those 14s cancel. This turns out to be VIY. So how could you generalize by looking at these two? What's a way you could make a statement for any angle, for any initial velocity? Maybe the initial velocity isn't 14. Maybe the angle theta is not 28. So what could I write just by looking at the two? What's the only real difference between them? Yeah, so x uses cosine and y ends up using sine. Okay, x uses cosine and y uses sine. So the generalization will be this. If you want to find out the velocity in the x direction, take the initial velocity, which was 14, and multiply by cosine theta. If you want to find the velocity in the y direction, take the initial velocity, 14, and multiply it by the sine of theta. And this is really what's important right here, this last box. Okay, that's what's important. That's how we break into components our initial velocity. That's how we take some quantity that's 14 at an angle and say, well, it's really maybe 11 up and 12 to the right. That's really what it's consisting of. Okay, and remember that the other day when we were doing cosine theta and sine theta, these were always giving you decimals, right? Like decimals less than 1 or something less than or equal to 1. So your legs, or your VIX and your VIY, are always going to be smaller than whatever VI was to start. So in this problem, we have 14 to start, right? What would you get for VIY if you did that? What's 14 times sine of 28? What's 14 times the sine of 28? What do you get? 14 times sine of 28. Just type it in your calculator. Make sure you're in degree mode, please. Make sure you're not in radian mode. And you can check that by hitting. 6.6. 6.6, all right? All right. So that's what we got for this one. And what did we get for 14 times the cosine of 28? 12.4? Okay. So take a look at the numbers, though. This is what I want to impart, or the part I want to really, hound on. The 14 is the largest leg of the triangle because it was the hypotenuse, right? And you know that just by looking up here at the triangle. If this is 14 up here, then these got to be less than 14. But once we start doing this throughout the year, you might forget that this always comes from a triangle. You're not going to have to ever redraw the triangle anymore. Okay, you're only going to have to use this knowledge at the end. But keep in the back of your mind that whatever you get for VIX and for VIY will definitely be less than what you had for VI. This number will always be a larger number than these numbers will, because technically speaking, cosine is it's really a ratio. You're taking a fraction of the initial velocity. That's what you're doing when you're multiplying by cosine theta. When you multiply VI times sine theta, you're really taking a fraction of the initial velocity, giving you VIY. Okay, giving you VIY. Now, somebody asked a question in the other class, which was a question that I'd like to repeat or just to discuss. And the question was, what is sine and what is cosine really? Okay, what are these things? What are they numbers? And the question was kind of posed like, is it like pi? Is it a constant? Sine and cosine are not numbers, they're functions. And what I mean is this. Here's what I mean. So make sure again, though, that you have this boxed in, right? This is our conclusion. But just like a little side note on the bottom in case you're wondering. If you ever had a table like x and y, and you were told, y equals 2x plus 1. If I pick numbers for x, I can get the values for y, right? If I plug in a 1 here, I end up getting 2 plus 1 is 3. If I plug in a 2 here, I get 4 plus 1 is 5. If I plug in a 3, I get 7. And I pick up on the trend that this goes up 2 because the slope is 2, right? So you notice this kind of stuff. So you've seen basic functions before. The sine and cosine are the same thing, really. So depending on what theta is, Okay? It's really like this. This is what sine and cosine really looks like. Really looks like theta, and then like something like this, sine theta. So depending on what theta is, you get a different value for sine. So I happen to know some of them, so I'll give you examples. If theta is 0, the sine of 0 is actually 0. The sine of 30 degrees turns out to be 0.5. The sine of, and these are ones that you're going to memorize. You'll know them, trust me, in math, not in physics. You'll learn them in math. Sine of 45 is 0.7071. The sine of 60 is 0.866. And you're going to learn that these are really just fractions. This is 1/2. This is radical 2 over 2. This is radical 3 over 2. But they're values, they're functions. It's like an input-output. So there's no one value for sine. There's no one value for cosine. It depends on what theta is. And that makes sense. Ready? Let me give you an example. I've got a launch pad, all right? Or I'm a punter in football. Either way you want to think about it works. Here's the launch pad at a low angle. The object is fired. What kind of a trajectory will it follow? What kind of a trajectory? Yeah, what's the word for that in math? What shape is this? Parabola, parabolic, right? So it would be a low parabola if it was a low angle. It might look like this, right? If I do this now, what happens? What happens to the projectile? It goes much higher, and it doesn't go as far now, right? Whereas a low angle might go further like that. Then there's something called an optimal angle, we'll talk about, which you might be able to guess as to what it is. But if I go all the way up to vertical, and I launch it, now I have one-dimensional motion. It's no longer in 2 dimensions. If I go vertical and I launch this, it does this. It comes right back down. Which is stuff that we've done already. The question on the test, remember when Josh tosses a coin up in the air and comes back down? That was the question. That's an example of just vertical motion. Or where James was ice skating and he came to rest. Well, he was only moving left to right. That was also just horizontal motion. So as this angle changes, you get more vertical or more horizontal velocity. So a low angle means that the VIX will be a larger number than VIY. A higher angle means that VIY will be a larger number than VIX. So as the angle gets closer to horizontal, you've got more of a push that way. As the angle gets bigger and bigger, and it almost opens up to 90, maybe like 85 degrees, it's more of an object that's launched up with a little bit of a movement left to right. So as the angle changes, the sine value also changes. Look at the values, they're completely different. And if you notice, look a minute ago, which function did we use for sine, for y you use sine, right? VIY is VI sine theta. And look at sine. Look what happens as the angle gets bigger. What's happening to this? Is it getting bigger or smaller? Bigger. Bigger, right? These numbers are getting bigger. 0, 0.5, 0.7071, 0.866. That's this, literally. Ready? Here's 0 degrees. Here's 30, 45, 60. When you get to 90, this actually, sine of 90 turns out to be 1. Okay, so as the angle gets bigger, the initial velocity is more in the vertical direction. For a small angle, though, the initial velocity is mainly in the x direction. But it's still a combination of both directions that we're really trying to figure out. Sure. Okay? Now, that statement at the top is really what you want to get from what we've done with trig. But I didn't want to just give you that statement to start. You shouldn't be like, what the heck is this cosine and sine stuff that we're doing? Because I know you didn't cover it last year. So I'm trying to give you a little background knowledge, but I'm not going into every intricate detail. It's just an icebreaker, that's all. So let's jot those down in big letters, or circle them, or star them, or whatever it is that you got to do. Easy way to remember. Just think about alphabetical. X comes before Y in the alphabet, and cosine comes before sine, right? Alphabetically. C comes before S, and X comes before Y. So if you ever forget which goes with which, just think about the fact that they are alphabetical in nature. Okay? I saw you were going to do it. All right.